Very good morning, students.
Good morning, sir.
Morning, sir.
Good morning.
Good morning. Let us start the discussion without wasting any time. Last class we have been discussed. This is the last point of discussion. Give reactivity order toward nucleophilic addition. So nucleophilic addition is going to be high whenever the electrophilicity of the carbon is high. So based on that, NO2 is electron withdrawing group, OH is electron donating, Cl is electron withdrawing. So because NO2 is a very good electron withdrawing group, it will increase the positive charge. Thereby, it will have greatest nucleophilic addition. So A, after A, we will be having C because chlorine is electron withdrawing, but not as great as NO2. And least electrophilic carbon is going to be in the presence of OH, which is electron donating group. So A, C, B is the right order. So then we have discussed that the chemical reactions of aldehydes we are going to start today. So different types of reactions we are going to have, and I have asked you to just go through the set of reactions which we have discussed in GOC. You have been through those reactions or not?
Yes, sir.
Yes, sir.
Yes,
Yes,
right.
sir.
So first aldehyde or ketone that will be reacting with HCl in the presence of basic medium. Why not acidic medium? So let's look at the reaction of aldehyde or ketone with a HCN, that is addition of hydrogen cyanides, or C double bond H, HCN in the presence of basic medium. We'll have this type of reaction, or C double bond O, CH, and HCN we are treating with a HCN we are treating in the basic medium. We form Cn minus and water. Cn minus will act as a nucleophile. It will try to attack the electrophilic carbon. As soon as it attacks, the pi electron density moves away. You get RCO minus CH CCN. This O minus will try to pick up the proton now. It will form RCOH CH CCN. Cyanohydrins. These are nothing but cyanohydrins. Whenever you try to add HCN to aldehyde or ketone, you will generate a cyanohydrin. That cyanohydrin can be, it can be depending upon the R group and hydrogen, it can be optically active or optically inactive. Because if R and hydrogen are same, let us say both are alkyl groups or both are hydrogens, in that case optically inactive. If a new chiral center is generated, if a new chiral center is generated, the cyanohydrin is going to be, the cyanohydrin will be optically active, and it form reciprocal mixture. It will form a reciprocal mixture. Why? Because you are getting two different enantiomers, 50% one type enantiomer and 50% another type. Mechanism is same, whatever I have discussed. Cyanide ion will be reacting the electrophilic carbon. As soon as it attacks, the pi electron density moves away. You get a tetrahedral intermediate. Initially, the carbon is sp2, which is trigonal planar. But now, as soon as the nucleophile attack, it becomes a tetrahedral intermediate. This tetrahedral intermediate, which have O minus that pick up the proton, again that will lead to the formation of cyanohydride and Cn minus. This reaction occurs very slowly with pure HCN. Why? It is a weak acid. This reaction occurs very slowly with the pure HCN because HCN is a weak acid. HCN is a weak acid, that's what. So whenever you take a basic medium, you will get more cyanide ion concentration, thereby increasing the reactivity rate. Is that clear?
Yes, sir.
Yes.
Yes, sir.
Yes, right. Now I have asked a question, why we should not do the reaction, same reaction in acidic medium? Acidic medium can also increase the electrophilicity of the carbon.
Common ion effect.
Yes, very good. Due to common ion effect, the dissociation of HCN will decrease, thereby decreasing the concentration of nucleophile. So we should not use acidic medium. Right. First example, what is going to happen in this case? Same. Cn minus will try to attack this particular carbon. C double bond to pi electron and moves away. Generate carbon connected to Cn and O minus. This will try to pick up the proton from HCN. It will form cyanohydrin like OH and Cn are present on the same carbon. This will be with respect to major product. Okay. They have given HCl. So even stronger acid, so easily the O minus can pick up the proton. A cyanohydrin is going to be obtained. Look at this case, CH3, C double bond to CH3, NaCN, Na plus Cn minus, NaCN is ionic compound, so Cn minus is obtained greatly. Cn minus attacks this particular carbon, pi electron and moves away, generate CH3, C, O minus, C, CH3, C, Cn, a tetrahedral intermediate, which will try to pick up the proton from the acid given, forming CH3, COH, C, CH3, CCN. Is it going to be chiral or achiral?
Chiral.
Achiral, because two methyl groups are same, so it is not a chiral carbon. A cyanohydrin is going to be formed CH3, COH, CCN, CH3. Next type of reaction is addition of NaHSO3. Addition of NaHSO3, NaHSO3 will have this structure S double bond O, S O minus Na plus SOH, NaHSO3. NaHSO3 is reacting with some alkyl group like carbonyl group or C double bond O, Cr dash, let us say. And can I say the lone pair of electron present on sulfur, they will be attacking the electrophilic carbon. But negative charge on oxygen comes into lone pair of electrons on sulfur attack, the pi electron moves away, generating what? RCO minus. This O minus will develop electrostatic force of attraction with Na plus, Cr dash, S double bond O, S double bond O, S OH. And now what happens? This O minus will pick up the proton. Internal proton transfer occurs. Why? RCOH, Cr dash, S double bond O, S double bond O, S O minus Na plus. So this is nothing but a white crystalline compound. Sodium hydrogen sulfide or sodium bisulfide will react with a carbonyl compound. Mostly the reaction will be with aldehydes or ketones. Aldehydes can react greatly. First point, understand this, students. Aldehydes can react easily with NaHSO3. Methyl ketones can also react. But if you take heavier ketones, they will not react. Why? Because of steric repulsions. Heavier ketones will not react due to steric repulsions. Methyl ketones can react. Okay, so reaction happened in such a way such that you are getting C carbon connected to some alkyl group R and R dash I have taken here, hydrogen is considered, O minus Na plus, S double bond O, S double bond OH. Now the proton transfer occurred in the second step. First step is nucleophilic attack. Second step is proton transfer. Why does the proton transfer occur? Why does the like O minus connected to carbon is picked up the proton from where? SOH is there, right? This proton has been picked up. This OH electron density is given to oxygen. That S double bond O minus Na plus is obtained. Why this proton transfer occurred means, look at the negative charge on oxygen, which is connected to C, that is carbon, which is connected to hydrogen alkyl group, and also look at the negatively charged oxygen connected to S double bond O. The negatively charged oxygen connected to S double bond O is resonance stabilized or not? Equivalent resonating structures. Yes or no?
Yes.
The negative charge on oxygen connected to S double bond O is resonance stabilized, whereas the negatively charged oxygen connected to CHR is not resonance stabilized. So negatively charged oxygen here is going to pick up the proton to develop S double bond O minus. So that is the reason why proton transfer occurred, because of resonance stabilization, and this particular product is a white crystalline product which is water soluble in nature. So two things you need to understand: aldehydes will react as well as methyl ketones. If you take heavier ketones, they will not react due to steric repulsions. And the internal proton transfer occurred. Why? Because of negative charge oxygen connected to S double bond O is more resonance stabilized when compared to the negatively charged oxygen connected to carbon, which has only CH and Cl group. And the position of equilibrium lies largely to the right hand side. Right hand side, the position lies means for aldehydes. For aldehydes, the position of equilibrium lies largely to the right hand side, whereas if you take ketones, the equilibrium lies mostly to the left hand side. Why? Ketones are less reactive. Why? Due to steric repulsions. Because NaHSO3 is not a simple group. It is also a bulky group. And alkyl groups, if they are more heavier ketones, they will not react with NaHCO3. Only methyl ketones can react. Almost all the aldehydes, aliphatic and aromatic react with NaHSO3 to form addition products. Few methyl ketones react with NaHSO3 to form addition products. This reaction is useful for separation and purification of aldehydes from heavier ketones. Look at this example. Which of the following can be distinguished using NaHSO3? 4 options have been given. Which can be distinguished using NaHSO3?
So
No one?
fourth one.
First option.
First
Sure.
option I have told you, methyl ketones can react. Methyl ketones. Aldehydes will react. Aldehydes react. Methyl ketones will also react. Aldehyde, aromatic or aliphatic, both are reacting. So this benzaldehyde will also react. Methyl ketone will react. Look at this third option. This is ethyl ketone. This is also isopropyl ketones, diisopropyl ketones. So both are ketones. They both are not going to be reacting. Fourth option, this is aldehyde. Aldehyde will react. Ethyl ketones will not react. So option 4 is the right option. Okay. So option 4 is going to be the right option because one is aldehyde, the other is a not a methyl ketone. It is a heavier ketone like ethyl ketone is there. Then comes addition of Grignard agent. After the addition of HCN and after the addition of NaHSO3, we have the addition of Grignard agent RMGX. RMGX reacts with a formaldehyde to form primary alcohol. RMGX reacts with aldehydes except formaldehyde to form secondary alcohol. RMGX reacts with ketones. After hydrolysis, they will form tertiary alcohols. So this is the set of reactions which you can study. So we can look at the reaction mechanism for the tertiary alcohol, let us say, like any generalized carbonyl group, R C double bond O C R dash plus R double dash MgX. R double dash will have a negative charge, magnesium will have a positive charge. R double dash minus, that will be acting as a nucleophile and it will attack the electrophilic carbon. It cannot act as a base. Grignard agent here cannot act as a base because there is no acidic proton. So R double dash minus will attack this particular carbon. C double bond of pi electron density moves away. You will generate what? R C O minus. The O minus will develop electrostatic force of attraction with MgX with the positive charge on magnesium. Carbon is also connected with R dash and new bond R double dash. This upon acidic hydrolysis, H plus in the presence of H2O, it will form RCOH CrCr double dash plus MgX and OH minus from H2O will develop attractions with the Mg forming MgXOH. So this is the type of alcohol which you are having. If you take formaldehyde, you get primary alcohol. If you take any other aldehyde except a formaldehyde, you get secondary alcohol. If you take ketone, you will get a tertiary alcohol. The same mechanism we have even discussed in the chemical methods of preparation of alcohols. If you take CH3 C double bond H, you will get a secondary alcohol, same mechanistic approach. CH3 MgBr, CH3 C double bond H forming CH3 CO minus MgBr, CH3 H plus in the presence of H2O form CH3 COH, CH3. If I replace this hydrogen with again methyl group like ketone, if I take CH3 C double bond CH3 MgBr H plus in the presence of H2O, you get tertiary alcohol. Is that clear, students?
Yes, sir.
Yes, sir.
Yes.
Formaldehyde, primary alcohol, aldehydes except HCHO, secondary alcohol, ketone, tertiary alcohol. Try to solve this question. Which of the following will react fastest with a methyl magnesium bromide? Methyl magnesium bromide CH3 MgBr. Which will react fastest? What was the order? Aliphatic aldehydes more reactivity, then aromatic aldehydes, then aliphatic ketones, then aromatic ketones. Look at option 1 and 2. Both are aldehydes. Option 3 and 4, both are ketones. First is an aliphatic aldehyde. Aliphatic aldehyde will be having the greatest reactivity. So option 1 is the right option. Right? Very good. Acetone is obtained by the hydrolysis of addition product of methyl magnesium bromide and methyl magnesium bromide CH3 MgBr and which compound? Acetone is obtained by the hydrolysis of addition product of methyl magnesium bromide and ethane nitrile, propane nitrile, acetaldehyde, acetone. Ethane nitrile, let us consider CH3, CH2, C triple bond N. Ethane nitrile is this one or CH3 C triple bond N? Ethane nitrile is CH3 C triple bond N or CH3 C triple bond N. CH3 CH2 CH2 C triple bond N is propane nitrile. Understand this ethane nitrile carefully. What is ethane nitrile?
CH2C triple bond.
CH3 because 2 carbons should be there, right? Here we have taken 3 carbons. That should be propane nitrile. It can't be ethane nitrile. So let us take CH3 C triple bond N. The CH3 C triple bond N I have taken with CH3 MgBr. So what is going to happen? CH3 minus MgBr plus CH3 minus will attack this particular carbon. The pi electron density moves away. You will generate what? CH3C, CH3, double bond N minus MgBr plus. This upon treatment with H plus, it will form CH3C double bond NH, CH3. This upon again treatment with H plus, lone pair of electron present on nitrogen, they will pick up the proton. So it will form CH3C double bond NH2 with a positive charge on nitrogen, CCH3. Water is then the reaction mixture which is acting as a nucleophile, acidic hydrolysis. So lone pair of electrons on oxygen attack this particular carbon, C double bond electron ST moves away. And this is an imine. Imine upon hydrolysis form respect to C double bond N is going to be converted to C double bond O. Let us look at the mechanism. CH3C, carbon connected to oxygen, 1 lone pair, 2 OH bonds, positive charge on oxygen, carbon nitrogen single bond, nitrogen has 2 bonds and nitrogen regain its lone pair, CCH3. OH bond is again polar, partial positive on hydrogen, lone pair of electrons on nitrogen picks up this proton, forming CH3C, OH, oxygen regain its lone pair, connected with NH3 with a positive charge on nitrogen, carbon connected with CH3. Lone pair of electrons on oxygen comes into CN bond is going to be lost. You will generate loss of NH3 and you will have CH3 C double bond O, CH3 with 1 lone pair, positive charge OH bond, loss of H plus occurs, generates CH3 C double bond O, CH3, which is nothing but your acetone. I have done this mechanism, but you can easily say whenever you are doing the imines, CH3 C double bond NHCH3, imines upon treatment with acidic hydrolysis immediately forms respective C double bond N is converted to C double bond O. Yes or no? Same reaction mechanism I have discussed even in Stefan's reduction, diol H reductions. Remember?
Yes, sir.
That's right. So you'll get respective ethane nitrile as the right option. What are A, B, C, and D? Cyclohexanone treated with CH3 MgBr treated with H plus. CH3 minus attacks this particular carbon, C double bond of pi electron and moves away. You generate CCH3, CO minus, that will pick up the proton to form compound A in this manner. COH, CCH3. Now HBr. HBr, what happens? Alcohol. Alcohols can easily react with HBr. Alcohol can easily react with HBr and HI. But if they want to react with HCl, what we have to add?
ZnCl2.
ZnCl2, very good. With the HI and HBr, they can directly react, but with the HCl, we have to add ZnCl2 in case if you want to distinguish between primary, secondary, and tertiary alcohol. Only tertiary alcohol can directly react with HCl. Primary and secondary alcohol do not react. So lone pair of with HBr, all types of alcohol react. Secondary alcohol, lone pair of electrons and oxygen attack H plus. As soon as they attack, you get CCH3. OH is going to be converted to OH2 plus, OH2 plus, and loss of bromide occurred. We form a carbocation. Yes or no? Only methyl and primary will undergo SN2. Secondary, tertiary, benzylic allylic will undergo SN1. SN1 is preferable here. So we form 3-degree carbocation. It's a tertiary alcohol, so 3-degree carbocation is formed. So Br minus will now attack, forming respective compound CH3Br. So this is your compound B, CCH3CBr. Mg in the presence of ether. So insertion reaction of alkyl with metals. It will form what? CH3 carbon bromine is now converted to carbon MgBr. This is your compound C. Compound C, Grignard reagent is treated with a HCHO followed by acidic hydrolysis. Grignard reagent CH3 MgBr will have negative charge on this carbon. It will be reacting with HC double bond OH. Negatively charged carbon attack this particular carbon, forms HCO minus CH, and ultimately it will form what? Proton is also there. O minus picks up the proton. So we have CH3 connected with a CH2OH. This is nothing but a D. A, B, C, D we have written. Okay. Same compounds we got everywhere. Is that clear, students?
Yes, sir.
Yes.
Right. Look at this question. Which of the following will react with HCN to form a racemic mixture? Which of the following will react with HCN to form racemic mixture? A new chiral carbon should be developed. OH and CN are going to be different, but the carbon should be connected with two different groups. Two hydrogens, not going to be chiral. Two phenyls, same. Two methyls, same. So obviously, second option. Okay, product should have chiral carbon. So CH3, COH, CH3OH, that will be the product which is going to have chiral carbon. So that will be the right option. And next type of chemical reaction is addition of alcohols. Addition of alcohols will form what? Addition of alcohol to aldehydes will lead to the formation of
Acetal, acetal and
Acetal.
hemiacetal.
acetal or hemiacetal. First you will get hemiacetal, that will again react with one more molecule to form acetal. With a ketone,
Ketal, hemiketal.
Ket-
hemiketal is obtained when 1 mole of alcohol reacted. Ketal is obtained when 2 moles reacted. Aldehyde reacting with alcohol in the presence of acid medium. Why this acid medium has been increased? Why this acid medium is required?
To increase the electrophilicity of carbon.
Very good. To increase the electrophilicity of the carbon, we require the acidic medium. So we form hemiacetal. Hemiacetal means one OH group and one OR group will be present. Again, H plus in the presence of ROH, it will form what? RCOR, COR, CH. And in this reaction, what is lost here? Is there something which is lost?
Water.
Water is lost. Since water is lost, can I say if I remove the water from the reaction mixture as soon as it is formed, the forward reaction is great or backward reaction is great?
Backward.
Forward reaction.
If I remove the water from the reaction mixture as soon as it is formed, the forward reaction will be happening greatly because the concentration of product is decreased. Reaction moves in the direction to form more product, which happens in the forward direction. Instead of that, if I add more water, what is going to happen?
Backward reaction.
Backward reaction.
Backward reaction happens. That means I can convert the aldehyde to acetal or acetal to aldehyde, I can do the conversion. This I have also explained, they are actually useful as a protecting groups. The reaction of like C double bond is their ketone. I can convert the ketone to cyclic ketol, protect it. Only I can make the reaction with other compound and I can add more water, form the ketone back. Like that, we are going to have some questions. We'll discuss that. So in hemiacetal, OH and OR groups attached to same carbon. In acetal, two OR groups attached to same carbons. So how the mechanistic approach can be understood? Hemiacetal means when one equivalent of monohydric alcohol react with aldehyde, one equivalent of monohydric alcohol react, monohydric alcohol it should be, it should not be a dihydric. In the dihydric alcohol, we have two OH groups. Both of them can react to form cyclic acetals. When one equivalent of monohydric alcohol react with an aldehyde, hemiacetal is formed. Acetal is formed when two equivalent of monohydric alcohol react with aldehyde, acetal is formed. And how the reaction is going to happen? R C double bond of CH plus H plus. First lone pair of electrons and oxygen, they attack the proton to increase the electrophilicity. We get R C double bond, only one lone pair OH bond and a positive charge on oxygen CH bond. Now this carbon is more electrophilic. So what alcohol being nucleophilic in nature, that will attack the electrophilic carbon. So let us take this alcohol as O18 oxygen or O18 OH. So lone pair of electrons and oxygen attack the carbon. Pi electron density moves away, generating what? Generating R carbon connected to oxygen, two lone pairs, OH bond, CH bond as it is. Carbon also connected with oxygen. Only one lone pair now. This is O18 oxygen and positive charge will be present. Oxygen connected to, let us say this is R dash, R dash, OR dash OH. Now what is happening, students? O18 oxygen possesses positive charge. So OH bond, electron density is moving towards oxygen. So lone pair of electron present on this oxygen picks up the proton. Or you can simply say loss of, because if I pick up the proton again, if I try to remove the water, I will be getting ketone or aldehyde again. So instead of that, if you try to remove the H plus, you will generate RCOH, CH, COR dash. This is O18. This is nothing but your hemiacetal. This hemiacetal again reacting with H plus in the presence of ROH. Loss of water occurs. RCH, COR dash O18, OR dash O18. This is R dash O18H. R dash O18H. Okay. So this is nothing but your acetal. So acetal and hemiacetal, they are going to be formed whenever aldehyde reacts with alcohol. When one unit or one equivalent of monohydric alcohol reacts, you get hemiacetal. When two equivalents of monohydric alcohol react, you will get acetal. Instead of aldehyde, if you take ketone, the same points you can write. One equivalent of monohydric alcohol react with ketone to form hemiketal. Two equivalents of monohydric alcohol react with ketone to form ketal. R C double bond or ketone, H plus in the presence of ROH, you get hemiketal. Again H plus in the presence of ROH, you get ketal. Hemiketal means when one equivalent of monohydric alcohol react with a ketone, hemiketal is formed. When two equivalents of monohydric alcohol react with a ketone, ketal is formed. Is that point clear? Same mechanistic approach again. And if we add more amount of water, the reaction proceeds in the backward direction. If we remove the water from the reaction mixture, the reaction proceeds in the forward direction.
Forward direction.
Right, very good. Mechanism, the same mechanism, whatever we have explained will be given here. Lone pair of electrons present on oxygen, they attack the H plus, increase the electrophilicity. ROH again act as a nucleophile, attack the electrophilic carbon. Loss of H plus occur to form a hemiacetal. Again H plus, you form OH reacting with H plus to form OH2 plus. Alcohol reacts, loss of water occurs, you generate this particular intermediate R C double bond O with a positive charge on oxygen. And now this carbon is going to be electrophilic carbon again. Again, R-OH will try to attack. Pi electron density moves away. You generate RCHOR and OROH with a positive charge on oxygen. Ultimately, loss of H plus occurs to form RCOR-COR-CH. This is nothing but your acetal. This is nothing but your hemiacetal. The same mechanism, electrophilicity increased, and then the alcohol acting as a nucleophile attacking the electrophilic center. Repeating the same steps again generates from hemiacetal to acetal. Reaction is carried out in the presence of acid like HCl, paratoluene sulfonic acid or concentrated sulfuric acid, so that the H plus ions can be reacting with a lone pair of electrons on oxygen to increase the electrophilicity. Why do we need to increase the electrophilicity? Why can't the reaction directly happen?
Because
we are-
OH is not that strong electrophile or nucleophile.
ROH is not a strong nucleophile. Very good. Earlier we have looked at cyanide ion. Cyanide ion directly attacked. HCN, in the HCN reaction, RC double bond OH, if you take reaction with HCN, CN minus directly attack the carbon. Pi electron density moves away. There we have not increased the electrophilicity. But here we are increasing the electrophilicity because ROH alcohol is a weak nucleophile. Very powerful electrophile. That is, whenever you add H plus to the C double bond O, whatever you're getting C double bond O, oxygen positive and OH, that's a very powerful electrophile where electrophilicity has been increased greatly. If I take a ethylene glycol, that means dihydric alcohol, in that case I'll be getting cyclic ketones. Look at the reaction. RC double bond OH, ROH excess. If you take ROH excess, you'll get what, students? RCOR, COR, CH plus H2O. RC double bond OR plus ROH excess means we have taken very high amount of alcohols. So directly you will get ketol and acetals. In the first case, whenever you have taken aldehyde, you get acetal. In the second case, where you have taken ketone, you get a ketol. Right? To shift the equilibrium in forward direction, H2O should be removed continuously. If you add H2O continuously, the equilibrium will be moving in the backward direction. That is what the same point I have been explaining. Like if you have taken RCOR, COR, CH plus H2O excess, if you are adding excess of H2O, what happens? Reverse reaction happens. The same first reaction has been reversed. These two are reverse. Okay. Reverse reactions or not? If I take H2O excess, I'll be getting aldehyde back and alcohol back. If I take alcohol excess and remove the water, then I'll be getting the forward reaction greatly. RCOR, COR plus H2O excess, like ketol I have taken, adding excess of water, then I'll be getting what, students? Ketone and alcohol. RC double bond R plus ROH is obtained. Trick, how to do the trick? RC double bond O CH plus R dash OH means we have to remove hydrogen from the alcohol and C double bond O oxygen. That oxygen you have to remove. 2 hydrogens and oxygen you have to remove, and that means you are removing water. This carbon has to be connected with OR dash and OR dash. That is what your acetal or ketol formation look like. RCH OR dash. This is how your acetal or ketol formation. If I replace hydrogen with a alkyl group, that will be a ketol. If I simply place that as hydrogen, it will be acetal. RC double bond of CH plus R dash OH will remove the water, forming RCOR dash COR dash CH. Try to do this example. Acetone reacting with ethylene glycol in the presence of H plus forms what? First step we can write it in this manner. Yes, how to write the shortcut? So CH3 C double bond of CH3 plus oxygen is connected with OH bond and CH2 OH, because it is a dihydric alcohol, not a monohydric. So hydrogens from the OH bond are going to be lost. Oxygen from C double bond is going to be lost. You will be generating CH3, CH3, CO, CH2, CO, CH2, CH2 are also connected. Cyclic ketol. And for this cyclic ketol, if I add more amount of water, what happens? We'll be getting ethylene glycol and acetone back. H2O excess. If I add excess H2O to the cyclic ketol, what I'll be getting? Acetone and ethylene glycol, they are going to be obtained back. This is a trick actually, but the mechanistic approach we have seen. First lone pair of electrons on oxygen, they will be attacking H plus, then lone pair of electrons on this oxygen attack, acting as a nucleophile. Like that, again this OH acts as a nucleophile, ultimately generating cyclic ketol. CH3, CH3, O, CH2, CH2, O. So cyclic ketols are going to be formed. I have told you one day that protecting groups, whenever you don't want the respective ketone group to be unaffected, that means the C double bond should not be affected. Then in that case, you can protect that particular C double bond by forming the cyclic ketol first. Then you can convert the other functional groups, and finally you can add a more water hydrolysis so that the cyclic ketol will be again converted to ketone group. Right on that point, cyclic ketol formations, cyclic ketols are even used as protecting groups. Yeah, this is what I'm saying. Acetals as protecting groups or ketols as protecting groups. This is what, students, C double bond group, right? This is a C double bond. It is an ketone, so you should be forming respective cyclic ketol. First, I have treated with OH CH2 CH2 OH. That means ethylene glycol. Then H plus ethylene glycol in the presence of acidic medium. What will happen? Ethylene glycol in the presence of acidic medium. What will happen? Will form respective cyclic ketol. Yes or no?
Yes.
This is how you can understand. The oxygen from C double bond and two hydrogens from the OH group, they are going to be lost. We will be generating the 6-membered ring as it is. Here it is connected with oxygen, oxygen, CH2, CH2. This is going to be formed. Cyclic ketol is going to be formed. The cyclic ketol, if you try to add water, what happens? In the presence of acidic medium, if you try to add water, you will get cyclic ketone again.
Ketone.
Try to solve this question. First, I have treated with ethylene glycol H plus medium to this particular compound. What happens? Here C double bond OR is what group? C double bond OR groups ester. C double bond is ketone. Ester and ketone, the lone pair of electrons on oxygen, they will be attacking the H plus first. And ethylene glycol is going to react with the C double bond O, not C double bond OR. Why? Why the ethylene glycol will react with ketone over ester? Because in ester, if you look at lone pair of electrons present on oxygen, they were in resonance with the C double bond pi electron density, decreasing the electrophilicity of the carbon of C double bond or not. In ester, the C double bond pi electron density is in resonance with the lone pair of electrons on oxygen. The lone pair of electron present on oxygen, that is in resonance with the C double bond pi electron density, decreasing the electrophilicity. So nucleophilic attack is never going to happen with respect to this ester over ketone. So ketone will also will always have greater tendency to react or to attack by the nucleophile. So what it will form first? It will first form this particular compound. Cyclic ketol is going to be formed with this as it is C double bond over. Now I am treating with LaLH4. Now I am treating with LaLH4. If I treat now with lithium aluminum hydride, what is going to happen?
Oxygen containing groups turn into alcohols.
Yeah, oxygen containing functional group will be converting into respect to alcohol. So this is an ester group. C double bond OR is going to be converted to respect to alcohol. So what is going to happen? The cyclic ketal will not be affected because the ring system, and you will have CH2OH formed. The ester oxygen containing functional group. Lithium aluminum hydride will try to reduce all polar functional groups, which contains all functional groups which contain polar pi bonds. NaBH4 reduces only 4 functional groups like aldehydes, ketones, acid halides, and imines. H2 in the presence of metal catalyst will reduce all polar and non-polar functional groups containing pi bonds except carboxylic acid. So you got the ester converting into LiLH4 to form respective CH2OH. So then you can treat with H2O. H2O in the presence of H plus, what is going to happen? The cyclic ketal will be converted to respective C double bond O CH2OH. Got this or not? The questions are not going to be in this fashion. The question how they are going to be asked is, they'll give the reagents, they'll give the substrate and product. I'll give the both the substrate and product. C double bond O, C double bond O OR converted to respect to this compound. C double bond O CH2OH. For the above conversion, the proper reagents used are option A, LiAlH4 in H2O. Option B, NaBH4 in H2O. Option C, H2 in the presence of palladium. Option D, CH2, CH2, OH, OH, and then these options. First set, second set LiLH4, and third set H3O plus. Which option you have to choose? And everyone got the question or not? The question is not like what is happening whenever this particular compound react with CH2, CH2, OH, H plus, LiLH4, H3O plus. The question is, I am doing this conversion, C double bond O, C double bond O OR2, C double bond O CH2OH, the same reaction. Useful reagents are, okay? Correct set of reagent is, which is the correct set?
D.
D.
Just now we have solved. Option D is going to be the correct set. But why can't option A? If I treat with lithium aluminum hydride will reduce all polar pi bond functional groups. Like C double bond O is an aldehyde group, is a ketonic group. That ketonic group will be affected by lithium aluminum hydride or not?
Yes, sir.
If I
Yes, sir.
take LiAlH4, the C double bond O is going to be affected. That C double bond O will be converted to what? LiAlH4, if I take that C double bond O will be converted to CHOH. And you have CH2OH. This is going to be obtained. You are not going to get this product. That means I have to protect the C double bond O group. Understood this point or not? I cannot directly
Yes.
use LiAlH4. I have to protect the C double bond O group. To protect the C double bond O group, I have to do this cyclic ketal formation. So option D will be the right option. That conversion, what are the correct set of reagents used for the above conversion means you have to check whether some of the functional groups are protected or not. Here C double bond is protected. If I treat with H2 in the presence of palladium, both are going to be again reacting. If I treat with NaBH4, NaBH4 will not reduce esters. If I treat with NaBH4, what happens? You will get a C double bond OR will be as it is, but this C double bond is converted to CHOH. Ketone will be reduced, but not the ester. When I treat with the fourth option, then only you are going to get the proper conversion. So that is how the questions can be generated. Look at this cyclic ketal formations, where it can be acting as a protecting group. It protects some of the functional groups. It's a very interesting, good question, right? Next, acetone is treated with excess of ethanol in the presence of hydrochloric acid. Acetone, CH3, C double bond O, CH3. Excess of ethanol. Ethanol is C2H5OH. C2H5OH. in the presence of hydrochloric acid. What is going to happen? Oxygen and these hydrogens are lost. You will get CH3, CO, C2H5, CH3, O, C2H5. What is going to form? Ketol is formed. CH3 taken by C, OC2H5, OC2H5. Option 2 is the right option, right? Sumangiri, lithium aluminum hydride can be in ether as well as in water. Lithium aluminum hydride reacts with water also. Okay, LaLH4 H2O means we have to do the same. LaLH4 can be ether also, having the same reaction. Okay, it can be both. Simply LaLH4 plus H2O, LaLH4 plus ether. In all the three conditions, we have to do the same reaction.
Sir, in water medium, it will explosive, no?
Yeah, explosively it reacts. The reaction is going to happen. The reaction will be happening fastly, explosively.
Okay, sir.
Okay, it produces H2 gas immediately. That H2 will be added to the respective polar pi bond. Immediately the hydrogens are going to be added. CH3, CCH3, OET, OET. Option 2 is going to be the right option. Next set of reactions, addition of H2O. So far we have seen reaction with addition of HCN, NaHSO3, alcohols, and Grignard agent. Then addition of water. If water is added to the respective aldehyde or ketone, what is going to happen? And again, what is the weak nucleophile or strong nucleophile? Whenever I am adding a nucleophile which is a weak nucleophile like water or alcohol, then I have to do the acidification to increase the electrophilicity of the carbon. Whenever I am doing the reaction with a strong nucleophile like HCN and NaHSO3, then I don't need to do the acidification. So what is a weak nucleophile? So I have to do the acidification so that the lone pair of electrons on oxygen are C double bond H treated with H plus. Lone pair of electron present on oxygen, they will attack the H plus, forming R C double bond O. One lone pair as it is OH bond formed, positive charge on oxygen CH, and water is now going to act as a nucleophile. This carbon is highly electrophilic, so lone pair of electrons on oxygen attack the carbon. Pi electron density moves away. We generate RC, carbon connected to oxygen. Oxygen has two lone pairs and OH bond, and a new carbon oxygen bond formed. Oxygen lost its lone pair, so positive charge CH. Ultimately, it undergoes loss of H plus ion to form what? R, C, CH, OH, and OH. You may ask, like, sir, two OH groups in the same carbon is unstable, but it is not under all conditions. Whenever these two OH groups are present on the same carbon, it is mostly unstable, but whenever they involve in intramolecular hydrogen bonding, then stability is gained. Same mechanism, RC double bond OH H plus, RCOH, COH, CH. Protonation of carbonyl compounds greatly enhances the electrophilicity of the carbonyl carbon. Obviously, protonation if you do, that will increase the electrophilicity of the carbon. So weak nucleophiles can also attack. Now the question is, which like geminal diols are formed. Geminal diols, like on the same carbon you have two OH groups. That is only stabilized under some set of conditions or only with few compounds. Like if you take formaldehyde, whenever you add to water, it will form HCOH, COHCH. A 37% solution of formaldehyde in water is called as formalin. Formaldehyde in water always exists in the form of geminal diol, not HC double bond H. Why? Because in formaldehyde, the two other hydrogens, they are going to be experiencing least steric repulsions so that this reaction can happen. But if you take acetaldehyde, you can look at the reaction. 58% will only in the diol form. Remaining will be in the respective CH3 C double bond H form. If you take ketone like acetone CH3 C double bond CH3 and add water, you will be having 99% in the respective ketone form and very least in the respective diol form. Higher steric repulsions. From top to bottom, what happens? Like HC double bond H, CH3 C double bond H, CH3 C double bond CH3, steric repulsions increased.
Yes.
Okay, because of increase in steric repulsions, the nucleophilic attack is never happening. So this is the first point. Whenever water acts as a nucleophile, for water to act as a nucleophile and attack the electrophilic carbon, the steric repulsions has to be low. Then only the nucleophilic attack is going to happen. If not, nucleophilic attack will not happen. Carbonyl compounds which form stable hydrates. I have explained one carbonyl compound to you earlier, if you remember, chloral hydrate. Like if you consider this CH2 C double bond or treated with H2O, it will form respective 3-member cyclic ring and OH groups are present. Relief in the angle strain. You will have a relief in the angle strain. Because of this relief in the angle strain, this diol is going to be major. Chloral, if you take, in the chloral you have intramolecular hydrogen bonding. Even though the chlorine and hydrogen develop partial intermolecular force of attraction, I am calling this as hydrogen bonding only. On what basis we can define that as hydrogen bonding? On what basis you are supposed to say it is a hydrogen bonding or it is dipole-dipole? It is not just atoms, not just between hydrogen fluorine, hydrogen oxygen, hydrogen nitrogen, or hydrogen and sp hybridized carbon. On what basis you are defining is, you are defining on the basis of amount of energy released. Whenever two molecules developed electrostatic force of attraction like hydrogen bonding, let us say, in that case the some amount of energy has to be released because system gains stability. Based on the amount of energy released, we call that as hydrogen bonding. Here, because of two chlorines, partial negatively charged chlorines developing attractions with a partial positively charged hydrogen, the amount of energy released is high. That's why we still call that as hydrogen bonding. Okay. It is also called as intramolecular hydrogen bonding only because the amount of energy released is in that particular order of amount of energy released for hydrogen bonding sites. You consider this case, like if you look at this particular C double bond O, if it convert to OH and OH, partial negative, partial positive, partial negative, partial positive. So two intramolecular hydrogen bondings. So because of that, it also exists in the diol form. COH, COH, partial negative, partial positive, partial negative, partial positive. Look at this compound. pH C double bond O, C double bond O, C double bond O. Like three C double bond O groups, whenever they are present on three adjacent carbon atoms, you have to always think of this diol with the middle carbon, middle C double bond O, so that it can form two hydrogen bonding sites. pH C double bond O, COH, pH C double bond O, COH, partial negative, partial positive, partial negative, partial positive. Yes or no? Greater the number of hydrogen bonding sites, greater will be the stability or not. Okay. Diols are stabilized due to intramolecular hydrogen bonding. And the same intramolecular hydrogen bonding we can also see in many biomolecules as well. If you remember DNA, in DNA, like in the double standard structure of DNA, do we have intramolecular hydrogen bonding between the bases or not?
Yes.
How many types of intramolecular hydrogen bonding is present between what type of bases? Like adenine, if you take, adenine will try to develop intramolecular hydrogen bonding with only
Guanine.
Time. Timing.
ATGC. Yes or no? Adenine and thymine, they will have how many hydrogen bonding sites?
Two.
Two. Guanine and cytosine will have
Three.
three. So that is how ATGC hydrogen bondings are going to be stabilized. Even in the biomolecules, we have the same intramolecular hydrogen bondings, or in some other polymers, we have van der Waals forces, sulfide linkages. All these forces are present. Addition of NH3 and its derivatives, the same reaction, RC double bond O plus NH2Z in the presence of H plus will form respective RC double bond N, NZ and H2O. RC double bond N, NZ and H2O is going to be obtained. And how is this reaction going to happen? And what type of acidic medium we have to maintain? We have an aldehyde group, RC double bond O, R dash. We are treating with a derivative of ammonia. So first, if I maintain the acidic condition, lone pair of electrons and oxygen, they attack the proton. As soon as they attack the proton, they will form R C double bond O, only one lone pair, OH bond and a positive charge on oxygen, and a C R group is also there. Now what is going to happen? The derivative of ammonia, like NH2Z, I am considering lone pair of electron present on nitrogen, they will attack this particular carbon. The C double bond of pi electron density moves away. R C R dash, carbon nitrogen new bond, nitrogen positive charge because it used its lone pair. Nitrogen connected with two NH bonds and NZ bond. Carbon connected with oxygen with two lone pairs and OH bond. Nitrogen bearing positive charge is unstable because NH electron density is moving towards nitrogen. So lone pair of electrons and oxygen picks up the proton. NH electron density is given to nitrogen. What will happen in that case? You have R dash, nitrogen regained its lone pair, NH bond as it is, and nitrogen also connected with Z group, and oxygen used its lone pair, so only one lone pair on oxygen, two OH bonds and a positive charge. So lone pair of electrons and nitrogen, they should come into Y, because oxygen with a positive charge is attracting the CO electron density, and H2 is a good leaving group. Loss of H2 occurs, we generate R C R dash C double bond N. Nitrogen used its lone pair again, so positive charge, NH bond as it is, NZ bond as it is. Loss of H plus ion occurs to form R C double bond N, C R dash NZ. Nitrogen regained its lone pair. So this is nothing but the addition compound of ammonia derivatives to your respective aldehydes or ketones. Aldehyde or ketone treated with NH2Z to form RCR dash C double bond NZ. This is addition compound. And what type of reaction is this? Addition elimination, because first addition occurred, lone pair of electron nitrogen attacked the carbon, addition occurred, then loss of water seen. Addition elimination type of reaction. In the nucleophilic substitution, where you can have addition elimination type? In which type of nucleophilic substitution we have addition elimination type reactions? Nucleophilic aromatic substitution reactions, if you look carefully. Yes or no? Nucleophilic aromatic substitution will be addition elimination type. In the nucleophilic aromatic substitution, what is the intermediate form? What is the complex called as? Messenhammer complex, carbanion type systems, which if the groups stabilize the Messenhammer complex, they will undergo nucleophilic aromatic substitution greatly. Electron withdrawing groups present at ortho and para positions stabilize the Messenhammer complex, thereby undergoing the nucleophilic addition reaction, nucleophilic aromatic substitution, that is addition elimination type at a greater rate. Okay, it is also similar addition elimination type. And pH has to be maintained 4.5 to 6. Why? Can I take a pH of 2? Because more fastly the attack is going to happen, lone pair of electrons and oxygen.
No,
Why
sir.
can't? Yes, I can take, Varshita.
No, sir.
Why?
Acid-base reaction can occur.
Very good. If pH is equals to 2 to 3, strong acid means acid-base reaction occurs. Acid-base reaction occurs. Can I maintain pH as like greater than 7? Electrophilicity of carbon not increased. If I maintain pH greater than 7, electrophilicity of carbon is not increased. Thereby the nucleophilic attack is not happening. Electrophilicity of carbon is not increased, right? In case of basic medium, you are not having the electrophilicity of the carbonyl carbon increasing. In case of acidic medium, strong acid medium, the strong acid react with the ammonia derivatives or bases, right? Acid-base reaction occurs. So you have to maintain weakly acidic medium. Weakly acidic medium has to be maintained. And the mechanism I have given, addition elimination type mechanism. Simply shortcut is remove oxygen and two hydrogens from nitrogen, remove water, you generate a double bond between carbon and nitrogen. R C R dash C double bond N Z plus H2O, that is the derivative obtained or addition product obtained. Look at this reaction. In all the cases, what is going to happen? The nitrogen, from the nitrogen, 2 hydrogens are lost, and from the C double bond, oxygen is lost. This oxygen and 2 hydrogens, these 2 hydrogens. Hydrazine, if you take, you will generate respect to hydrazone. If you take hydroxylamine, NH2OH is hydroxylamine in acidic medium, you are doing the reaction weakly acidic medium. C double bond oxygen from the C double bond O and 2 hydrogens from the NH2, they are going to be lost because you don't need to write the mechanism always. You can simply write the product. CH3, C double bond N, OH, that is oxygen is obtained. CH3, C double bond N, NH2, hydrazone is obtained from hydrazine. If you take aniline, CH3, C double bond N, connected with CH5 group. If you take primary amine, there you get CH3, C double bond N, CH2, CH3. These are nothing but your Skiff's bases. The details of Skiff's reagent we'll discuss. Oxygen from the respective C double bond O and 2 hydrogens connected to nitrogen, they are going to be lost. That is a trick. Here you have to write the respective addition products. Write down here what is going to happen. Phenyl hydrazine, NH2, NHPH. The oxygen and 2 hydrogens are going to be lost. CH3, C double bond N, NHPH is going to be obtained. Phenyl hydrazine to phenyl hydrazone. 2,4-DNP, 2,4 dinitrophenylhydrazine. NH2, NHPH is phenylhydrazine. On the second and fourth positions of phenyl group, you have NO2, 2,4 dinitrophenylhydrazine react with the respective carbonyl compound to form CH3, C double bond N, NH, C6, H3, NO2, NO2, which is a colored complex. Like aldehydes will be reacting with the 2,4-DNP to form respective colored complexes. With the semi-carbazide, which NH2 is going to be reacting? These 2 hydrogens are lost or these hydrogens are lost, like A set, B set?
A set.
A set, because in the compound B, the lone pair of electrons and nitrogen, they were in resonance. So that cannot be acting as a nucleophile. So semi-carbazide to semi-carbazide is going to be reacting and it will form semi-carbazone. Why you are writing phenyl hydrazone, semi-carbazone, hydrazone? Because water is lost. Water is actually lost. Is everything clear, students, so far?
Yes, sir.
Yes.
Yes, right. Look at the example. The oxygen and 2 hydrogens, they are going to be lost. You will be generating this 5-member ring C double bond N, NH, C double bond NH2. That's what happened. So directly that is the product. Substrates given, product also given. So they should at least ask what is the product, right? So this is a product, okay, which was asked. Mechanism, we know, lone pair of electrons and nitrogen, they attack the electrophilic carbon, pi electron moves away, then the whole elimination occurs of water. Elimination of water occurs in the final stage. Addition elimination type reaction, weakly acidic medium. Addition elimination type reaction, weakly acidic medium, and respective water is lost. So whatever the compound you are writing, that you should be ending with one. Hydrazone, semi-carbazone, phenyl hydrazone, like that. These are all the reactions of carbonyl compounds with respect to ammonia and derivatives. Stereochemistry of nucleophilic addition. What happens in the stereochemistry? If a new chiral carbon is generated or if a new chiral center is generated, we will be having formation of racemic mixture. CH3, C double bond H, HCN OH minus will generate like we have C double bond. Initially we have trigonal planar. Cn minus is a nucleophile. The nucleophile can attack from the top or it can also attack from the bottom. So top attack will give to different enantiomer. Bottom attack will give to other enantiomer. So non-superimposable mirror images are obtained, which are said to be enantiomers. They are obtained in equal proportions. So you will end up with racemic mixture. Okay, if one is R, for racemic mixture, if one compound has R configuration, the other should be
S.
yes. So whatever the number of chiral carbons we have, it doesn't matter. At every chiral carbon, if the stereochemistry has been exactly reversed, then it is said to be racemic mixture. Then it is said to be enantiomers. If a stereochemistry is differed at a few carbons, but not at all, what are they called as?
Diastereomers.
Diastereomers. At every carbon, if stereochemistry is same, then they are said to be identical,
Identical.
right? So this is the two different chiral carbons. If one is going to be S, the other is R. So they are said to be enantiomers, and the mixture, total mixture is said to be a racemic mixture is obtained. Reduction of aldehydes or ketones. What are the reducing agents you can use? LiAlH4 in water. LiAlH4 same you can write in ether, solvent. NaBH4 you can use in ether or water. And you can also use H2 in the presence of palladium or metal catalyst. So these are the reducing agents you can use, and you can convert the respective aldehyde or ketone. Aldehydes or ketones are oxygen containing functional groups. The oxygen containing functional group will be converted to respective alcohol. So reduction to alcohols, RC double bond O CH, LiLH4 in the presence of H2O, it will form what? NaBH4 in the presence of H2O, H2 in the presence of palladium and charcoal. You get hydrogens are going to be added simply. Pi electrons you have to remove, you have to add hydrogen here and hydrogen here. So you get RCH2H, which is nothing but primary alcohol. So aldehydes will react with the lithium aluminum hydride or NaBH4 or H2 in the presence of palladium and carbon, will form respective primary alcohol. If I take ketone, same set of reactions, what I'm going to expect?
Secondary
alcohol.
Secondary alcohol is going to obtain. RCHOH, Cr is going to obtain. Simply hydrogens are going to be added, students. The mechanism for reductions and oxidations are not, they are out of your 12th standard. Very lengthy mechanisms. Because in the process of reaction, a 6-member transition state is obtained. What happens whenever LiAlH4 is attacking the C double bond O, you will get a 6-member transition state which actually exists in the chair form. So that is why those mechanisms we are not discussing, because they are out of your standard. So aldehydes and ketones, they will be reacting with the reducing agents like lithium aluminum hydride in water, NaBH4 in the water, or H2 in the presence of metal catalyst to form respective primary and secondary alcohols. Lithium aluminum hydride, LiLH4, sodium borohydride is NaBH4, Na plus BH4 minus, Li plus AlH4 minus. Now the question is, from where you are getting the hydrogens added? Understand this point carefully. CH3 C double bond H treated with LiLH4 in water. Which hydrogens were adding? I'm not adding hydrogens from water. I'm adding the hydrogens whatever you are going to add to C double bond O. Yes or no? Look at this carefully. The hydrogen whatever you are adding to C double bond O carbon is the hydrogen from LiLH4 or NaBH4. From this reaction, you can just look at the color change. Lithium aluminum hydride as Li plus AlH4 minus. From this, the hydride ion is now going to act as a nucleophile that will attack the electrophilic carbon. Understood this point or not? So the hydrogen connected to carbon is obtained from reducing agent, lithium aluminum hydride or sodium borohydride. The pi electron density moved away, you get negative charge on oxygen. This negatively charged oxygen picks up the proton, that will be from water. Understand this point? Lithium aluminum hydride generates the hydride ion that will attack this carbon, pi electron density moves away. The negatively charged oxygen picks up the proton from the water. Okay, although we write in the simple ways, actually the transition state looks like 6-member transition states. Understood this point or not? CH3 C double bond O CH is converting into CH3 CH2OH, but the hydrogen added to oxygen is obtained from water. The hydrogen added to carbon is obtained from reducing agent like lithium aluminum hydride or sodium borohydride. Look at this reaction, CH3 C double bond O. Like let us place the isotopes. You may get confused here. Like if I take LaLH4 in the presence of D2O, you will have the simple reaction. Instead of colors, we can keep the isotopes, right? You answer this case, CH3 C double bond O CH3. I am treating this with LiAlD4, treating with H2O. LaAlD4 produces D minus ion deuteride ion that will attack as the electrophilic carbon C double bond of pi electron density. Moves away. CH3CO minus CdCH3. This will attack water H2O. Lone pair negatively charged oxygen picks up the proton, forming CH3COH, CCH3Cg. Got it now? The questions can be interlinked with respect to by the introduction of isotopes. I can ask different types of question. Lithium aluminum hydride is providing the hydride ion which is acting as nucleophile. H2O is providing the proton, it is not the hydride ion added. Solve this question. CH3, CH2, C double bond O, CH3, palladium in the presence of charcoal H2. This H2 gas is now going to be added. Adsorption is going to happen here. The H2 gas is going to be added. That means the hydrogen is added to carbon as well as oxygen. You get CH3, CH2, CHOH, CH3. Here it's not like LaLH4 or NaBH4. It is the H2 gas, right? Here adsorption is going to the mechanistic approach. The hydrogen atoms, they are going to be added to carbon as well as oxygen of C double bond O group, generating respective alcohol. Try to solve it. What you will be generating? Yes or no? H2 in the presence of palladium or carbon or charcoal, that will reduce both the polar pi bonds as well as non-polar pi bonds. So C double bond C will be converted to here hydrogen added, here also hydrogen added, C double bond O, here also hydrogen added, here also hydrogen added. So we'll generate this as a major product. So which is the right option then? I think in option 2, positive charge should not be there. Okay. Reduction of aldehyde or ketone, reduction to hydrocarbons. What are the reactions which you can study here, students? Reduction to hydrocarbons.
Clemenson reduction, Wolff-Kishner and red phosphorus.
Clemenson's, Wolff-Kishner, right? And red phosphorus also can think. Like C double bond is going to be converted here. In the Clemenson's reduction, do we use Clemenson's reduction means zinc amalgam in the presence of concentrated HCl. Zinc amalgam concentrated HCl means do we need to use respective acid sensitive functional group? If it is there, then can we use this? Zinc amalgam concentrated HCl. Can I use this particular reagent whenever we have acid sensitive functional group?
No, sir.
No, we should not use. So C double bond group is going to be converted to respective CH2. Aldehydes or ketones, whenever you treat with zinc amalgam in the presence of concentrated HCl, they will form respective CH2 group, C double bond to CH2. Aldehyde or ketone, whenever they treat with respect to NH2 NH2, they will form respective C double bond and NH2. That will be treated with KOH upon heating in the presence of ethylene glycol. It will form again CH2. So these are the different types of reactions which you can see in the conversion of respective aldehydes or ketones to your respective alkane systems. Aldehydes and ketones, they have been converted to alkane systems. How is that conversion happening? Like the Clemenson's reduction, we don't go with the mechanistic approach, but Wolff-Kishner we can think. We have R C double bond O R dash converted to R C double bond N NH2 R dash. This Wolff-Kishner reduction, first is a reaction of aldehyde or ketone with ammonia derivatives. We form respective hydrazine to hydrazone. From this hydrazone, whatever the reaction we are having, base upon heating and ethylene glycol, base will try to pick up the proton. Base NH2 C double bond N NH2 is there. Base will try to pick up the proton. OH minus picks up the proton. As soon as this proton is picked up, NH electron density is given to nitrogen. R C double bond N NH with a negative charge on nitrogen R dash. Negative charge on nitrogen comes into C double bond, electron density moves away. R C R dash, negative charge on carbon, N double bond NH. Again you have NH bond. The NH electron density is going to be picked up by carbon. So we get R CH R dash N double bond N. This NH electron density is given to nitrogen again, so we get negative charge. So negative charge nitrogen comes into C single bond nitrogen, electron density is given to carbon, generating R CH minus R dash plus N triple bond N. This will try to pick up the proton from water. Like alcohol is also there, proton can be picked up, forming R CH2 R dash. Okay, don't worry with the mechanistic approach and all, but this is how the things can happen. R C double bond R dash, that is aldehydes or ketone treated with the zinc amalgam in the presence of constant HCl, will form respective alkanes treated with NH2 followed by KOH on heating and ethylene glycol, forms respective alkanes. These are nothing but your respective Clemenson's reduction and Wolff-Kishner reductions. Clemenson's reduction you should not use whenever acid sensitive functional group is there. It is not preferred. Not preferred whenever acid sensitive functional group is there, and Wolff-Kishner is not preferred whenever base sensitive functional group is there. Base sensitive functional group, whenever it is present, whenever we have base sensitive functional group, we should not do Wolff-Kishner reduction. Whenever we have acid sensitive functional group, we should not do Clemenson's reduction. Right? Example, you do it. Here only C double bond, I can do Clemenson's, I can also do Wolff-Kishner, no issue with that. Okay, I can do Clemenson's reduction, Wolff-Kishner reduction, convert the C double bond O to CH2. Because there are no other functional groups except C double bond O. Do this example. Can I do Wolff-Kishner and Clemenson's both? Can I do Wolff-Kishner and Clemenson's both in this particular reaction?
It's a Wolff-Kishner.
Why can't Clemenson's? There is no other functional group, right? Except C double bond, or do we have any other functional group?
Yes.
No, right. There are no other functional group, so I can do Wolff-Kishner reduction or Clemenson's both. I will be generating respective C double bond or converting into CH2. Yeah, this is what, if acid sensitive group is present, then Clemenson's reduction should be avoided. If a base sensitive group is present, then Wolff-Kishner reduction has to be avoided. With respect to that also, we'll look at the example. Look at this. Which of the following is useful for the given conversion? C double bond along with C double bond we have OH. So lone pair of electron present on oxygen, they can be attacking the H plus ion, where H plus is there. Whenever we do the Clemenson's reduction, we have acidic medium. In that condition, OH is acid sensitive or not? OH is not affected actually if you look at the conversion. OH is unaffected. OH unaffected means if I take acidic medium like Clemenson's reaction, then OH will be affected. So acidic medium, if I take, OH will be affected, but OH is unaffected here. So Clemenson's you should not use. Wolff-Kishner you have to use. Got it now?
Yes.
So OH is acid sensitive functional group. So you are not going to use Clemenson's reduction. Wolff-Kishner reduction you have to use. Go with this particular intermediate substrate. Chlorine is there. Along with C double bond you have chlorine. Clemenson's you can use, but Wolff-Kishner you cannot use because Wolff-Kishner has base. Base can try to pick up the proton undergoing elimination. Okay. With the base, in the presence of base, it can undergo. In the presence of base, elimination can occur. Elimination is possible. So Clemenson's reduction is the only correct choice. Clemenson's reduction is correct choice. Right? Look at this compound A and B. What is compound A? CH3, C double bond to Cl, AlCl3, benzene. Friedel Crafts acylation you are doing. So C double bond to CH3 aldehyde or ketone.
Oh, ketones.
So respect to acetophenone is obtained. That acetophenone treated with a Zn zinc amalgam in the presence of constant HCl. C double bond converted to CH2. So CH2 CH3 ethyl benzene is obtained. Phenol. You cannot say phenol. In the presence of phenol, you should have OCH2 CH3. So ethyl benzene is going to obtain C6H5 CH2 CH3. Okay, these are different types of reactions. What are the reactions so far studied? Can you list out? No one. With HCN. So I'll be listing out. Just check it out. Any other any reaction I have missed out? With HCN we have seen. NaHSO3 we have seen. With alcohols. With Grignard agent. With water. With ammonia derivatives. And last reaction. Reductions LaLH4, NaBH4, and also Clemenson's and Wolff-Kishner reductions. So far we have seen these reactions, right? 7 reactions. And the next set of reaction is oxidation of aldehydes or ketones. This oxidation of aldehydes or ketones will be happening in the presence of aldehydes can be oxidized in the presence of milder oxidizing agents. What are the milder oxidizing agents for aldehydes? If I treat alcohols, primary alcohols with the milder oxidizing agents, I'll get carbonyl compounds. What are the milder oxidizing agents you are going to use for primary alcohols? PCC, PDC, CrO3, anhydrous. Yes or no? Like that you will be using. But aldehydes or ketones can be converted to respective acids or carboxylates. That conversion can happen in the presence of milder or stronger oxidizing agents. But for aldehydes, we can use milder oxidizing agents only, stronger not required. For ketones, we require stronger. Why? Because in aldehydes, if you look at CH3, C double bond O CH, CH3, C double bond O CH3 is a ketone. In aldehyde, we have a oxidizable hydrogen. In aldehyde, oxidizable hydrogen is present, whereas in ketone, there is no oxidizable hydrogen. So that is why oxidation of aldehydes occurs in the presence of milder oxidizing agents. What are the milder oxidizing agents? Tollens reagent, Fehling's and Bendick solution, we can say. Oxidation of aldehydes you can do with strong as well as mild, but oxidation of ketones you have to do only with strong. With the milder oxidizing agents, you cannot oxidize ketones. First one, oxidation of aldehyde with strong oxidizing agents like K2Cr2O7, Na2Cr2O7, H plus and HNO3. So respect to C double bond H, K2Cr2O7 in the presence of H3O plus, what happens? You will get respect to carboxylic acid because acidic medium. Strong oxidizing agent in acidic medium will form carboxylic acid. Strong oxidizing agent in basic medium will form what? Carboxylates. Because the base, whatever there, that can pick up the proton from the acid, forming the carboxylate salt. So benzaldehyde treated with a K2Cr2O7 in the presence of H3O+, which will form what, students? C6H5 C double bond OH is going to be obtained. That means oxidizing agent added the oxygen. Got this or not?
Yes, sir.
Yes.
Strong
Yes.
oxidizing agents will be reacting with both aldehydes and ketones to form respective carboxylic acids or carboxylates. When the carboxylic acids are going to be formed, whenever we have acidic medium, when the carboxylates are going to be formed, whenever we have basic medium. With a strong oxidizing agent, this reaction is going to happen. Same CH3, CH2, C double bond O, CH, chromic oxide. Whenever you treat with H2SO4, in the acid medium, CrO3 will behave as a strong oxidizing agent. Jones reagent, this one, CrO3, consonant H2S4, acetone. So it will form respect to C double bond OH will be converted to C double bond OH, CH3, CH2, C double bond OH is obtained. Oxidation of ketones with a strong oxidizing agent follows which rule? Popoff's rule. Like if we want to oxidize ketone, the oxidation of ketone takes place according to Popoff's rule. What Popoff's rule says? The C double bond group lies with the smaller alkyl group. Because in the oxidation of ketones, we have to cleave the carbon-carbon bond. That means I can have, if I have unsymmetrical ketone, then I have to cleave that carbon-carbon bond in such a way such that C double bond will be lying with the smaller alkyl group. So Popoff's rule states that during the oxidation of unsymmetrical ketone, but during the oxidation of unsymmetrical aldehyde, we are not cleaving the carbon-carbon bond. Understand that point. In the oxidation of aldehydes, we are just cleaving carbon-hydrogen bond. That is why they can be oxidized with the milder oxidizing agents also. But ketones will be oxidized only with the stronger oxidizing agents. Popoff's rule states that during oxidation of unsymmetrical ketone, the cleavage of carbon-carbon bond, that is carbon-carbon, which carbon? This is a carbon connected to C double bond O. That is cleaved in such a way such that keto group always stays with the smaller alkyl group. The keto group always stays with the smaller alkyl group. Which bond is cleaved? A, B. Which bond will be cleaved?
A.
Read the statement again.
B is clear.
C double bond O should lie with the smaller alkyl group. C double bond O should lie with CH3. That means the other bond has to be cleaved. B will be cleaved. And if it cleaves, you get CH3, C double bond OH, CH3, C double bond OH plus CH3, C double bond OH. This bond cleaved, right? This carbon connected to two hydrogens. Again, oxidation occurred because strong oxidizing agent is there. So you get this carbon also converted to C double bond OH. This carbon also converted to C double bond OH. Do it here. Two cleaves A, B. Which bond can be cleaved?
B.
B, because C double bond should be lying with smaller alkyl group. So you'll get what? CH3 C double bond OH, CH3 CH2 C double bond OH. CH3 C double bond OH, ethanoic acid and propanoic acid are obtained. Understood?
Yes, sir.
Yes or no? So this is the oxidation of aldehydes or ketone with the stronger oxidizing agents. So next class we can go with this Tollens test, failing solution, bending solution. These are all milder oxidizing agents. Only aldehydes can be reacting. In the aldehydes also, which type of aldehydes will react? Aliphatic or aromatic, under what conditions? All that we'll discuss in the next class. So only aldehydes, that is milder oxidizing agents, can be reacting only with aldehydes, not with ketones, because in ketones there is no oxidizable hydrogen. Got it now, students?
Yes, sir.
That's right. Right. Thank you all, everyone. Bye.
Thank you, sir.
Thank you, sir. Thank you, sir.